Let's talk about the intermediate value theorem. This is the very first of the big theorems of calculus, at least for my classes. The intermediate value theorem is actually not even a calculus theorem. It's more of an algebra 2 type theorem. The only condition is continuity. But here are a few examples of using the intermediate value theorem. The first one's more real world. I have a 2-year-old son. When he was born, he weighed 7 pounds. Now he weighs 34 pounds. So using the intermediate value theorem and my supreme genius, I can conclude that at some point between birth and today, he weighed 15 pounds. That's the intermediate value theorem. I went from 7 to 34, had to cross 15 somewhere. So a more mathy example. So let's say we have a continuous function and continuity is key to use the intermediate value theorem. So we have a continuous function that travels from the point 1, 3 to the point 5, 8. And if you want to visualize that, I'm going to draw a crap graph here. So we have the point 1, 3. I go from this point to the point 5, 8. I go up here. So I go from this point to that point, and I am continuous. At some point between x equals 1 and x equals 5, this function must hit a y-coordinate of 5. 5 being somewhere between 3 and 8, and it is impossible for me to connect those 2 points with a function and not hit a value of 5. If I go linearly, I obviously hit it. If I go, if I try to say really low and then sneak up really quick, still doesn't work. Even if I sneak up there really quickly, you got to hit 5. The only way you wouldn't hit 5 is if you do something really silly like go all the way around, but now we're no longer a function. We failed the vertical line test. So any continuous function that goes from one point to another must hit all the y values in between. So let's look at a more math definition, a mathy definition here. So if f is continuous on the interval a to b, and f of a is not equal to f of b, and that's kind of one of the things you have to remember is we must travel from one y-coordinate to a different y-coordinate. So I'm going from a to b, and f of a is simply the y-coordinate where the function begins on the interval. F of b is simply the y-coordinate where the function ends. So we have a continuous function that connects those 2 points, and n is some number that lies between f of a and f of b. So n is somewhere on the interval between f of a and f of b, and it could be anywhere. We could slide that anywhere you want to. There must be, at some point between a and b, some value of c where f of c is equal to n, and this is exactly what I just said a minute ago with the points 1, 3, and 5, 8. This is just more generic. So if I connect a to b, doesn't matter how I connect them, I must hit this y-coordinate of n somewhere. So that y-coordinate of n, I will cross that line at some point, doesn't matter how I connect them. You could cross more than once. You're not guaranteed only one. You could cross multiple times, but you will absolutely cross that value of n somewhere. And as I have it drawn right here, my c would be that point. And it does so happen that I found an f of c that equals n. So that is your math definition of the intermediate value theorem. And it does rely on continuity. Now, one more thing about continuity as it applies to calculus. We have talked about differentiability, which means you can find the derivative at a point. And it turns out that if a function is differentiable, then it must be continuous. If a function is differentiable, it absolutely must be continuous. So sometimes a function will be described not as being continuous, but they will describe the function as differentiable. And in that case, you need to immediately recognize that the function is continuous. Now, the other way around, what if they say a function is continuous? Must that function be differentiable? And no, it may not be. So continuous functions, the other way around, continuous functions are not necessarily differentiable. Not necessarily. And I'm going to be lazy here. I'm going to say diffable. And the best example for a continuous function that is not differentiable would be a function with a cusp. It could be the absolute value v. But those are continuous functions. However, you are not differentiable at a cusp. So if they tell you the function's continuous, it may not be differentiable. However, if they tell you the function is differentiable, it will be continuous. As a matter of fact, some people describe differentiability as smooth and continuous. There's a little bit of a flaw with that, but I'm not going to worry about that now. So let's look at some math definitions or some math examples, some specific cases of using the intermediate value theorem. So let's say we have the function f of x is this quadratic, and we want to show that f of x does indeed equal 7 somewhere between -1 and 3. First thing I'm going to do, anytime you are showing something through a theorem or a proof, you have to establish the conditions that allow you to use that theorem. In this case, the condition that allows you to use the intermediate value theorem is that f of x is continuous. And because f of x is a polynomial, we do know that f of x is continuous. You absolutely must establish the conditions. On the AP exam, if you don't establish f of x is continuous or f of x is differentiable, if that applies to other theorems, you will be docked a point. You have to write f of x is continuous. Then we can go into the rest of the proof. So now my proof is going to be f of -1. I'm going to find f of -1, and I'm going to find f of 3 and hope that those values straddle the desired value of 7. So f of -1, 2 times -1 squared minus 3 times -1 plus 1 is going to be 2 plus 3 plus 1. That is 6. If I plug in 3, 2 times 3 squared minus 3 times 3 plus 1. That's 18 minus 9 plus 1 is 10. There we go. So now I can say that f of -1 is less than 7, and I am going to focus on the value that I'm trying to achieve. F of -1 is less than 7, and f of 3 is greater than 7, and I can say that because I've established their values already. Therefore, f of x equals 7 somewhere. We don't know where, we just know that it happens somewhere on the interval -1 to 3. And that is your intermediate value theorem. If you want to cite the theorem, you could say by the IVT. You don't necessarily have to do that. You do have to, you must include that the function is continuous. You have to actually write that if you are using the intermediate value theorem. Let's move on to this one. Let's see, am I hiding any words? No, I'm not. All right. Show that this function has at least one root, and a root is a fancy word for an x-intercept. And an x-intercept means that we need to show that the function is actually equal to 0. The function is actually equal to 0. So I'm going to do the exact same thing I just did. I'm going to start by establishing that the function f of x is continuous. Once again, we have a polynomial, so f is continuous. Then I'm going to find f of 0 and f of 1. F of 0 is going to be 0 plus 0 minus 3. F of 1, 1 plus 5 is 6. Minus 3 is positive 3. And I straddled my desired value of 0. So now I can say f of 0 is less than 0. And f of 1 is greater than 0. Therefore, f of x equals 0 somewhere, we don't know where, somewhere on the interval 0 to 1. So that's the way you solve these with the intermediate value theorem. Now, for these two examples we just did, for numbers 1 and number 2, you could have actually said, if I want to show that this function equals 0, I could actually just set the function equal to 0. Or I could just say, okay, x cubed plus 5x minus 3 equals 0. Solve the equation and see if the solution is between, or see if you have any solutions between 0 and 1. However, in this case, I wrote this one so that solving that would be very difficult. Solving x cubed plus 5x minus 3 equals 0, you can't factor it. There actually is a quadratic formula equivalent for cubic functions, but it is absurdly ugly, and I don't even know it. I've just seen it and said, I don't want to learn that. Now, number 1, we could have set that one equal to 0. We could, or not 0, but 7. We could have said 2x squared minus 3x plus 1 is equal to 7. And that one we can solve relatively easy. If it does not factor, you could quadratic formula that and then just see if either of the two solutions fall between -1 and 3. Now, we already know it happens because we've proven it by the intermediate value theorem. But if all they're asking you to do is show that the function equals a value, I would go intermediate value theorem. I would not go through the algebra. That's going to actually a little bit too far. If you solve this equation, you're not only showing that the function equals 7, but you're also showing where the function equals 7. Yes, that's a little bit more. That's a better answer. But why show off? We only need to show that the value occurs. And so if you have an explicit equation for the function, you do have that option of setting the equation equal to the desired value. However, on the AP exam and on my tests and quizzes and in AP calculus world, you very frequently will have a situation where it's impossible to solve the equation because they don't give you one. So here, what I've done is I've given you a table of values. It represents the velocity in feet per second of somebody running on a straight track. They do tell you that the velocity is a differentiable function. If a function is differentiable, we automatically know that that function is continuous. I'm going to make a note to myself. V of t is continuous. Okay, select the values for v are given, and they want you to show that the velocity equals 12 somewhere on the interval, somewhere on this interval 0 to 10. I probably should have included on the interval 0 to 10, but that's kind of superfluous. Okay, so this one's going to be actually pretty easy because we don't have to find the values. They've given us the values, and I can see that on the interval 5 to 10, I travel from 10 to 13. You could also look on the whole interval 0 to 10, where we go from 0 to 13. Both of those cases, heck, we could even go from 8 to 13. In all of these, doesn't matter how you grab the interval, I'm going from one side of 12 to the other side of 12. Therefore, I must hit 12 somewhere on this interval. And so I see that I can do this, and I'll just focus on the whole interval. I'm going to go from 0 to 10. But before you cite the intermediate value theorem, you must establish the condition needed to use the intermediate value theorem, which is continuity. Now, they didn't say explicitly that the function's continuous. We have to use a little bit of our understanding of differentiability. So I'm going to actually write v of t is differentiable. And because the function v of t is differentiable, we know, or you could say, therefore, v of t is continuous. So I now have established differentiability. I've now established continuity based on the differentiability that was provided. I can also see that v of 0 is equal to 0, which is less than 12. That's the value I'm interested in. And v of 10 is equal to 13. That is greater than 12. Therefore, v of c must equal 12. We don't know exactly where it happens, but it happens somewhere between 0 and 10. And you actually could narrow it down to between 5 and 10 if you wanted to use that interval. But I'm going to say v of c is equal to 12 somewhere on the interval 0 to 10. I'll say for some c on the interval 0 to 10. And that is typically how intermediate value theorem questions are asked on the AP exam. The other ones are rarer. You don't see the ones with explicit equations on the AP exam, but maybe in Algebra 2 Pre-Cal, you'll see problems like numbers 1 and 2. So there is my explanation of the intermediate value theorem.